Welcome to this presentation on the composite curve number, prepared by Marty Wanyalista and presented through BMPFast. The composite curve number is a method used to calculate the volume of runoff water when you have a combination of different soil and cover types across a watershed. The key idea is that storage occurs within those soil and cover areas themselves. When dealing with impervious surfaces like pavement, where there is essentially no storage, those areas must be handled separately from the composite calculation. However, it is worth noting that runoff from an impervious area can be directed onto a pervious area, as long as that pervious area has sufficient storage capacity to manage the additional flow. This presentation focuses on calculating the composite curve number, commonly referred to as the CCN, and walks through the calculation methods using a real example project. To set some foundation, the maximum potential storage of runoff, designated as S', defines the upper boundary of how much water a watershed can absorb before runoff begins. The formula for S' is 1,000 divided by the curve number, minus 10. To put that in practical terms, when the curve number is 78, the maximum storage is only 2.8 inches, meaning the soil has relatively limited capacity to hold water. On the other hand, when the curve number drops to 50, the maximum storage jumps to 10 inches, indicating a much greater capacity to absorb rainfall before generating runoff. One of the key learning objectives here is understanding that the composite curve number must be based on volumetric discharge, not a simple arithmetic average of individual curve numbers across a watershed. As we work through the example project, it will become clear why using a simple arithmetic average can lead to inaccurate results when estimating runoff volume. One of the most frequently asked questions in hydrology is when it's appropriate to use a composite curve number, and answering it properly requires a solid understanding of what the curve number actually represents. The curve number, or CN, is directly related to the maximum soil storage capacity, referred to as S', measured in inches. The relationship is expressed as S' equals 1,000 divided by the CN, minus 10, and this applies when the CN falls between 30 and 100. This means the CN isn't just an abstract index, it's tied to how much water the soil can physically hold. To make this concrete, consider a soil with a water holding capacity of 20%. For a soil profile 5 feet deep, that works out to 1 foot or 12 inches of storage. Plugging that into the equation gives a CN of approximately 45.45. That connection between soil depth and CN value is critical to understanding when composite curve numbers are valid. Looking at a few examples really drives this home. The CN of 30 corresponds to over 9 feet of soil depth needed to hold that water. A CN of 50 corresponds to about 4 feet and 2 inches. A CN of 78 corresponds to just over a foot. And a CN of 95, which represents essentially impervious surfaces, corresponds to only about 2.5 inches of storage. The key insight here is that for a truly impervious surface, 2.5 inches of storage simply doesn't exist in a meaningful physical sense. The CN for impervious areas is used to calculate runoff or rainfall excess, but any surface storage drains between events rather than representing true soil storage capacity. This distinction determines when a composite curve number is appropriate. The CCN is valid and useful when all the land cover areas being combined can actually store water. If one of those areas is impervious and cannot store water, you must not use the composite curve number approach. Doing so would misrepresent the true runoff potential of the watershed, because you'd be averaging together soil storage values where no such storage physically exists on the impervious portion. Here's an important concept to understand when working with curve numbers across multiple soil and cover types. You should never use a simple arithmetic average of curve numbers to calculate composite runoff. Let me walk through a concrete example that demonstrates exactly why. Consider a catchment in Zone 3 with 52 inches of annual rainfall and 2 soil and cover types, each covering 12 acres. The first has a curve number of 80, and the second has a curve number of 30. When you calculate runoff separately for each area and then add the results together, you get 6.760 acre-feet per year from the first area and 0.416 acre-feet per year from the second, giving a correct total of 7.176 acre-feet per year. Now watch what happens if someone takes the shortcut of simply averaging the two curve numbers. 80 plus 30 divided by 2 gives 55. Using that composite curve number of 55 in the calculation produces a total runoff of only 3.848 acre-feet per year. That is dramatically lower than the correct answer, and it would lead to seriously undersized stormwater management facilities. The right approach is to calculate runoff volumes separately for each soil and cover type, and then back-calculate the composite curve number from the total runoff volume. In this example, working backward from the correct total runoff of 7.176 acre-feet gives a composite curve number of 67.4, not 55. BMPFast can perform this calculation for you through its Tools menu and CCN calculator, and you may see a slight difference due to rounding, but the result should be very close. The fundamental rule here is straightforward: never average curve numbers directly. Always base your composite curve number on cumulative runoff volume. This is a screen capture from BMPFast showing the annual runoff coefficient values for Zone 3, organized as a function of both the non-directly connected impervious area, or NDCIA, and the percent directly connected impervious area, known as DCIA. The tool is designed to work in multiple directions, meaning you can calculate any one of the three factors if you know the other two. In the example shown here, the DCIA was known to be 0%, and the annual runoff coefficient was given as 0.069. Using those two known values, BMPFast calculated the NDCIA as 67.4%. One important thing to note is that BMPFast handles the interpolation automatically, so you don't need to manually look up and interpolate between table values yourself. However, if you do want to reference the underlying data, the full table values are available in the Applicant's Handbook from 2024. BMPFast provides another convenient way to calculate the composite curve number. Starting from the Watershed Characteristics worksheet, you can navigate to the Composite CN calculator. In this case, we're working with the post condition, though there is also a separate Composite CN calculator available for the precondition. Once you're in the calculator, you simply enter the area and curve number data for each land cover type in your watershed. After entering all the values, BMPFast calculates the composite curve number based on the volume of runoff, and in this example, that result comes out to 67.5. Composite curve numbers, or CCN, come into play when a drainage area contains more than one soil type, and those soils are capable of providing maximum storage through the curve number calculation method. The key thing to remember here is that you should never use a simple arithmetic mean to calculate the CCN. Instead, the correct approach is to calculate the total runoff volume across all the areas and then back-calculate the CCN from that volume. This ensures your result is grounded in actual discharge behavior rather than a simple average that could lead you to an inaccurate answer. When it comes to performing the calculation itself, you have a few options. You can work through it by hand, use the BMPFast software through the Tools menu, or use the Composite CN calculator. All of these approaches follow the same volume-based methodology. The example calculations provided throughout this material are there to help you apply these concepts confidently to your own analyses and real-world projects. Work through those examples carefully, because they are your best guide when you encounter similar situations in practice. That brings us to the end of this presentation on the composite curve number by Marty Evangelista. We hope this has given you a solid understanding of how the composite curve number applies to runoff volume and soil storage within the BMPFast framework. You are encouraged to explore other learning modules, and when you are ready, you can apply to take the competency test. For details on that process, please refer to the module called Self-Test. Thank you for watching.